In this module of Chapter 2 on life tables, Module 2.5, I will cover abridged life table concepts and construction. An abridged life table is an abbreviated version of a complete life table in that it lumps age classes. This type of life table retains all of the basic functions, properties, and concepts of the basic life table, while at the same time removing two disadvantages of the complete life table. First, it reduces expense. It is often extremely expensive or virtually impossible to monitor mortality in a cohort over their entire life course in the short intervals required to construct a complete cohort life table. This constraint is especially relevant to life table studies of small invertebrates and rodents. Second, it reduces unnecessary details. By grouping deaths into age increments larger than a single age, it is possible to summarize the information more concisely. Notation and concepts. In a complete life table, the basic parameters apply to a single age interval. For example, the parameter P10 implies survival from age 10 to 11. However, in an abridged table where the interval of concern is greater than a single age class, a subscript n is used to designate its length beyond age x. For example, npx, nqx, and ndx denote period survival, period mortality, and death frequency, respectively, in the interval x to x plus n. This notation is also used to denote the number of life years lived by the cohort in the interval as nlx, based on the formula shown here. For the computation of expectation of life at age x, which is based on the remaining life years to be lived by the average individual alive at age x, an additional parameter tx is needed, which is the sum total of remaining life years. This column is then used to compute remaining expectation of life in an abridged life table given by the equation EX equal TX over LX. Construction of abridged cohort life tables. Here I provide example computations for constructing an abridged life table using the data presented for the complete life table on Drosophila melanogaster. Column 1 contains age class X from 0 to the oldest age. Column 2 contains the number alive at age X, denoted NX. Column 3 contains cohort survival to age X, denoted LX. This is computed the same as in the complete life table, where LX is the dividend of NX and N naught. Column 4 contains the fraction surviving in an age interval NPX. This is the proportion of flies alive at age X that survive to age X plus N. In the example, 10px is the proportion that survived from age x to age x plus 10. Here's example computations for the abridged table px. In words, 0.9851 of all flies age 0 survived to age 10, and 0.4457 50-day-old flies survived to age 60. Column 5 contains the fraction dying in the age interval NQX. This parameter is the proportion of those alive at age X that die in the interval X to X plus N. Here are example computations for the abridged table QX. In words, only 0.0149 of the newly eclosed flies died before they reached age 10, but 0.5543, or over 50%, of the 50-day-old flies died before reaching age 60. Comparing 10-day age intervals, flies were 37 times more likely to die in the 10-day interval from 50 to 60 days than in the interval from 0 to 10 days. Column 6 contains the fraction of the initial cohort dying during an age interval NDX. This column contains the fraction of the original cohort that die in the age interval X to X plus N. Here are example computations for the abridged table dx. In words, 0.0149 of the entire original cohort died between age 0 and age 10 days, but between age 50 and 60 days, 0.1415, nearly 15% of the entire cohort died. Column 7 contains life days lived in an interval x to x plus n, denoted NLX. Here are example computations for the abridged table parameter LX. Column 8 contains the cumulative days lived by the cohort beyond age x, denoted TX. Here are example computations for the abridged table parameter TX. Column 9 contains expectation of life at age x, EX. This is the expected number of additional days the average fly age x will live, denoted EX. Here are example computations for the abridged table EX. In words, average newly eclosed flies and 50-day-old flies have respectively 39 and 10.9 days of life remaining. The reduction of the number of age classes from around 80 ages in the complete life table to only 9 age classes in the abridged life table preempts the study of the details of mortality trajectory at older ages. However, in many applications, researchers are primarily concerned with life expectancy comparisons. Therefore, it is useful to understand the extent to which accuracy of this metric for a complete life table is traded off to include lumped age classes, in our case 10-day age classes. From 0 through 50 days old, the absolute differences between estimates of expectation of life at age x for the two types of tables are small. For example, the values of E0 and E10 for both tables are identical. However, at 50 days and beyond, the relative differences in life expectancy estimate range from moderate to large. For example, E60, E70, and E80 differ by 0.7, 1.6, and 3.8 days respectively, with all differences in favor of the abridged table estimates. The reason for this discrepancy is that because of the rapid decrease in survival, the rectangle method of life day estimation overcompensates to the right of the midpoint. Note in this schematic that when survival is flat, the wide rectangle estimates the life days under the curve exactly. When it is decreasing at a constant rate, the wide rectangle used for estimating life days under the curve is also accurate because the life days underestimated under the actual survival curve are offset exactly by the life days that are overestimated outside of the curve. However, when survival is decreasing at ever-increasing rates at older ages, the magnitude of the underestimate will be overcompensated for by the overestimate outside of the curve, as shown in this schematic. This completes Module 2.5. In the next module, I will compare period and cohort life table concepts and metrics.